So here we have our D3 questions, and starting with number 1, let's go. Okay, so size of the universe, it's the cosmic scale factor being R, and so we have a formula for Z relating to the size of the universe being Z equals size of the universe R over the size of the universe R now over the original size of the universe when the light was first emitted, R naught, minus 1. And so that gives us size now over size then equals Z plus 1. So Z is 0.11. So 0.11 plus 1 is 1.11. So if we flip that to size of the universe then over size of the universe now, we get 1 over 1.11 or 0.9 or 90%. And then it says, how is Hubble's law related to Z? Well, we know that Z is equal to the speed, the redshift, Z, is equal to the speed of the star over the speed of light. And we know that the speed of a star is given as the Hubble constant times the distance to that star. So if we sub in the two V's together, we get that the Z shift, the Z's redshift, is given as the Hubble constant times the distance to that star over C. And then 2A and 2B are the, copies of 1A and 1B. 1A and 1B must have been the HL version. And then 2 is the, the SL version, and 2 is the HL version because we have 2C here. All right, 2C, it says that Hubble thought that galaxies were actually moving away and that redshift was caused by the Doppler effect. But then it was like, now we know it's cosmological redshift. Well, what the heck is cosmological redshift? Well, redshift is still a lengthening of wavelengths, of a shift towards red, towards longer wavelengths, but it's not because of relative velocity and the Doppler effect. It's because the cosmos itself is expanding. And if the cosmos is expanding, then any light that is within that cosmos also expands. And expanding light means a longer wavelength. So that's what cosmological redshift is. All right, so here's 3A. So for 3A, the Mark scheme explains it pretty well. It says the spectra of galaxies are redshifted compared to spectra on Earth, true, and then that redshift either is galaxies moving away, that's because of Doppler shifting, galaxies recede moving away from us, or redshift is interpreted as cosmological expansion of space. As space expands, the wavelengths that are in space are also going to expand. And if those wavelengths expand, they head towards longer wavelengths, hence the redshift. I would say that is the HL explanation that they would really be looking for. That's what Hubble, I think, figured out. So there you go. Sometimes the Mark scheme gives a satisfactory answer, sometimes it needs some explanation. But that was 3A. Let's go to 3B. All right, so we have a redshift from 122 nanometers to 392 nanometers. And based on that shift, we can figure out the relative size of the galaxy. We have two equations here. And so the relative size of the galaxies, R over R naught, is, that's what they're looking for, the ratio of the present size to the size when it's emitted by the galaxy. So that's R over R naught. And we have the original wavelength from the source that corresponds to 122 nanometers, but the redshifted line is 392 nanometers. So 392 minus 122 is 270. And then, so we have 270 over 122. Top. Okay, I think I just noticed that the camera frame was set to portrait when it should have been landscape. So, just kind of going back, here's 1A. Here's stuff from 1A and 1B. 1A, 1B, the mark scheme for 1B. And then 2A and 2B are repeats, but then we have 2C here about cosmological redshift. And then 3A, the mark scheme pretty much explains 3A. Does a pretty good job of that, so I'll let it speak for itself. Then 3B is what we were currently working on. And now our picture frame is working and we can get back to business. Okay, yes, we were comparing redshifts, figuring out the relative size of the universe, size now to size then, and so we have relative size is equal to the wavelength shift of the original wavelength plus 1. And so we wind up with an answer of 3.2. Technically it's 3.21 because we actually have 3 significant figures, which is unusual for an IB question. So 321. And that is the ratio of the present size of the universe to what the size of the universe was when the light was emitted. All right, 3C, age of the universe in seconds using a Hubble constant of 60 kilometers per second per megaparsec. All right. All right, so for number 3C, it gives the Hubble constant, again, as 70 kilometers per second per megaparsec, when we really need the Hubble constant in 1/seconds, because the equation relating the age of the universe to the Hubble constant is t is roughly 1 over the Hubble constant. Well, the Hubble, if the time is going to be in seconds, then the Hubble constant needs to be in 1/seconds, not kilometers per second per megaparsec. So we got to convert it. So we already have the 1/seconds. What we need to do is get rid of the kilometers per megaparsec. And really that they cancel, they're both measurements of distance, so they will cancel, but we pretty much have to convert megaparsecs to kilometers. Or meters. Why convert to kilometers? Let's do meters. So there's our kilometer, 23 meters, and then a parsec in meters. No, I don't think we know parsec in meters. I think we even know parsec in light years, right? And then we got to convert from that to meters. Let me look at the data table. Doobie constants. Doobie. We have, where's parsec? Where is it? I'm just pause this thing. And we're back. I found, yes, it's going to be parsecs to light years and light years to meters. Good times. All right. So there's the 1/megaparsec. There's parsec to light year, and there's light years to meters. So parsecs cancels, light years cancels, meters cancels. And so there we go. Once we've converted the Hubble constant into 1/seconds, then it's just simply 1 over the Hubble constant to get our time as 4.41 times 10 to the 17 seconds. Actually 4.4, since the original number was 70. So we'll say 4.4 times 10 to the 17 seconds. All right. In 3D, I think the mark scheme explains it well. It says, estimate assumes the present rate of expansion was always that rate of expansion, which is probably not true, but I would also, I think most important point here is the uncertainty in the value of h naught. That's not a very well-known number, so we can get close, but like for instance, I don't know that we could get down to like, the age of the universe in seconds, or at least, like 2 significant figures. But as I, joked the other day in class when they said that, the age of the dinosaur skeleton was 50 million years old and 6 months, because that's when the security guard started his job. It's like, it's not literally 50 million years to the month. It's that's an estimate, right? So yeah. And that was number 3, so here's number 4. All right, so number 4, the first 2 parts are identical to 3A and 3B. But 4C, let's see. Yeah, that's interesting. And 3C is different than 4C. 4C gets into critical density. And actually, the remainder, 4C, 4D, and 4E, are actually D5 questions, not D3 questions. I want to focus on D3 here, so I'm eliminating those as well. D5, D5, D5. And that brings us to number 5. Okay, number 5A is a legit question. To do 5A, we're going to do that the speed of a galaxy is equal to the Hubble constant times the distance away from us. And so here's the speed, 3.48 times 10 to the 6 meters per second, which matches the Merck. All right, 5B has to do with a redshift based on the speed of the galaxy. All right, I had to do that twice because I thought the speed of the light was 3 million meters per second, not 300 million meters per second. I caught my mistake. And so I have 492 nanometers is the new observed wavelength. Examiners report they obtained a blue shift. What the what? It's all about the redshift. Anyway, so 5C, moving on. In fact, when you look at that, talk about all about the redshift, that's the answer to 5C. How observations of spectra from distant galaxies provide evidence that the universe is expanding. That's because they all exhibit redshift. So, well said, Mark Scheme. All right, that was number 5. Let's go to 6. Number 6 is a good question, but it is not D3, it is D4. D4. So, we will see that when we look at D4. We're looking about type 1A and type 2 supernova, which are important, but it's topic 4, not topic. I'm sorry, it's D4, not D3. I want to focus on D3. Here's number 7. Now, 7A and B are, in fact, D3 questions. Okay, so we have speed versus distance for galaxies, and 7A says, how did Hubble figure out the recessional velocities of galaxies? So he did that based on redshift. And then using the redshift that he measured from those galaxies, then you could either use Doppler equations, or more fitting for D3, he used the z, the redshift, the change in the wavelength over the original wavelength is equal to the speed of the galaxy over the speed of light. And then this is where the Hubble constant comes from, by the way. The gradient of this line, the relationship between speed and distance from Earth, is equal to that Hubble constant because speed is Hubble constant times the distance away from Earth. In fact, that's how 7B works, using the graph determined in seconds the age of the universe. Well, first of all, the gradient, like I said, gradient equals the Hubble constant. Let's find the gradient. So those are my 2 points, 2-point slope. So when we go out to the slope of this line, we get 0.067 meters per second per parsec. Now we want to know the age of the universe in seconds. So we're going to have to convert parsecs to meters to cancel the meters. So we're going to get to 1/seconds. And then once we got that Hubble constant down to seconds, or seconds to the -1, then 1 over that is the age of the universe, 4.6 times 10 to the 17 seconds. And that was number 7. It looks like 8 is the same thing. It says use the age. Yeah, what does 8C say, though? Oh, it doesn't. 8 is literally the same question. I know it didn't assign 8, but I'm going to knock it out anyway as being a repeat of number 7. And so I'm going to split it there because there are 14 total questions. 14 total questions. and the homework I assigned was only 1 through 7 anyway, which just got significantly cut back because of other topics and repeats. So there you have it.